So welcome everybody. Thank you so much for being here. Today is our last seminar for the semester, and it's a pleasure to have Stephanie LaMassa here today for our last seminar. So Steph is a staff scientist at Space Telescope Science Institute, where she serves as the branch manager of the JWST Nearest instrument team. Steph earned a bachelor's degree in astronomy and physics at Boston University. And then she worked as a mission planner for the Chandra X-ray Observatory for several years before starting graduate school at Johns Hopkins. And then after earning her PhD from Hopkins, she moved to Yale University as a postdoc. And then she returned to Maryland as a NASA NPP fellow at NASA GSFC, and finally moved to Space Telescope in 2017. And she became branch manager of the JWST Nearest team in 2019. And Steph is an expert in AGN demographics using wide area multi-wavelength surveys. And you're going to hear a lot about that in today's talk. And she's done a lot of X-ray modeling of obscured AGNs, and I've really enjoyed her papers on that. She studies the connection between AGN and star formation in galaxies. And she also works on the observational constraints on the duty cycle and lifetime of AGN. And she's done some very nice work on changing look AGN that I've really enjoyed reading. And on top of all of that, she does a lot of outreach and really has a talent for communicating her enthusiasm for science to the public. And many of you probably know she runs the Astronomy on Tap in DC, so you should go. And I've had the pleasure of collaborating with her in recent years on JWST programs, and I'm really delighted, and she's a vital collaborator. And so I wanted to also say that she has a very interesting cat that I've heard about. And every time I Zoom with her, I hope that I see this cat, who apparently can open the door, can reach the doorknob and beg for food. So, maybe this amazing cat will make an appearance today. So with that introduction, I'll turn it over to Steph.
All right, thanks a lot, Shabita, for the great introduction. Hopefully the cat won't make an appearance. I just fed him, so hopefully he'll be quiet and maybe taking a nap, so that way we can get through this without him being too distracting. So let me see if I could find, now I've lost like the button for screen share. I think you might have made me co-host, and there's all these extra buttons here that
I made
not
you
used
co-host. Sorry.
that I'm not used to seeing. Oh, here we go. All right, it's okay. I found it. All righty, so I should be sharing the desktop, and I'm now in slideshow. So are you all able to see my screen?
Looks good.
Yes.
Excellent. All right, so let's go ahead and get started. Obscured AGN are really important if we want to understand cosmic evolution of supermassive black hole growth and the role that they play in shaping the galaxies that they live in. We know that the majority of the local AGN population is obscured. So if we want a complete census of black hole growth, we have to make sure we can identify these objects and understand their characteristics. And some obscured AGN could play an important role in determining the fate of their host galaxies. And one way that AGN might turn on and may be linked through their host galaxies is through galaxy mergers, where two massive galaxies interact. They lose angular momentum via dynamical friction. Torques then drive gas to the centers of the galaxies, triggering both circumnuclear star formation and AGN activity. At this time, lots of dust is also funneled to the centers of these galaxies, so this activity is largely obscured. Upon coalescence of these galaxies, the black holes themselves also merge, and starburst and AGN activity continues. And in this zoom in from the simulation from Phil Hopkins, we could see the nuclear region, which shows the gas spiraling into the black hole. So at this point, the AGN is intrinsically luminous, even if that activity is largely obscured. And within this framework, powerful winds are launched from the accretion disk, sweeping up mass and outflows. And this could be a process by which galaxies regulate AGN, regulate galaxy growth. These winds could perhaps evacuate gas from the galaxy altogether, or heat up gas and prevent it from cooling and forming stars. So in this paradigm, there's a short-lived phase where the AGN is heavily obscured and intrinsically luminous, and providing feedback into its host galaxy. Those winds will eventually clear out the enshrouding gas, revealing an unobscured AGN. And I'm sure as many here are aware, there are open questions about the relative importance of this process in both the cosmological framework of AGN triggering and galaxy growth. But to answer this question, we need to identify AGN that are in this stage, quantify the incidence rate to really have an understanding of how important this is and what role that plays in both the overall process of feeding black holes and in galaxy coevolution. So while obscured AGN are among the most interesting objects in the universe, they are challenging to identify, especially compared to their unobscured counterparts. And these are some excellent visualizations from a recent review paper from Ryan Hickox and Dave Alexander. So we all know that for the unobscured AGN, these are these very bright things that could be bright enough to outshine their host galaxies. And we see lots of ultraviolet and optical emission from the accretion disk. We see broad emission lines from near the black hole. We see really strong X-ray emission, mid-infrared emission from the AGN Taurus that is absorbing, the dust there's absorbing accretion disk photons and re-emitting in the infrared. But then once we have the obscured sources, we attenuate that strong optical and UV emission in the broadline region. We can use narrow emission lines. Those are very powerful diagnostics in the optical, but those are really only efficient in the lower universe. Beyond a redshift of 0.5, those emission lines are now observed in the infrared. And we don't have large area databases of infrared spectroscopy like we do in the optical. And we also know that these diagnostics evolve with redshift and they evolve with metallicity. We could use X-rays to identify these objects, but even then the X-ray emission could start being extinguished as obscuration increases. And another really powerful probe is to use the mid-infrared emission, especially in these very powerful AGN, because as we could see, that mid-infrared emission from the AGN Taurus dominates over the host galaxy. So we could use mid-infrared colors that parameterize this power loss slope that we observe from the AGN heated Taurus to select these objects. The caveat is that this really only works when the AGN dominates over the host galaxy. Once the AGN becomes weaker, the mid-infrared emission is really dominated by star formation. And then it becomes more challenging, especially in the infrared, is this balancing act between wanting to identify as many AGN as possible while minimizing the contamination of star-forming galaxies in these samples. And here we could also use X-ray emission, but again, it's going to be much weaker than we observe in the unobscured AGN. And once the column densities get above the Compton-Thick regime, it becomes very challenging. So any one multi-wavelength selection method has benefits, but it also has biases. And it's by combining samples selected across these multi-wavelength methods that we get the most comprehensive view of supermassive black hole growth and evolution. And it's by using surveys that we identify a representative sampling of AGN at many redshifts across the parameter space of redshift and luminosity to really understand supermassive black hole growth and evolution. So to address a major gap in our understanding of obscured black hole growth, over a decade ago, my collaborators and I began a wide area X-ray survey in the STRIPE 82 region of the Sloan Digital Sky Survey. And for anyone here who has worked with X-ray surveys knows when you take observations with an X-ray telescope, what you detect for each source are a handful of X-ray photons. And you have information about the energy of the X-ray photons, but to really understand what those objects are, you need multi-wavelength information. And this is why we chose the STRIPE 82 region. We wanted to do an X-ray selection because X-rays are the most efficient way to detect AGN. Anything above an X-ray luminosity above 10 to the 42 is powered by supermassive black hole accretion. Normal star formation processes don't form X-rays that energetic. And this gives us a way to identify obscured AGN that we miss in optical surveys, though it's more difficult to detect the most obscured Compton-thick AGN. And we wanted to do a wide area survey because that's the only way to discover rare objects, or at least a representative sampling of rare objects. And these include high luminosity AGN at high redshift. And though these objects are rare, they are important. Many models indicate that the majority of mass accretion onto supermassive black holes occurred when AGN are in this intrinsically luminous phase. And it may be these obscured intrinsically luminous AGN that are playing a role in galaxy evolution. So in 2010, when we began this X-ray survey, there hadn't yet been wide area X-ray surveys between 0.5 to 10 keV. We had excellent X-ray surveys that are deep pencil beam surveys like GOODS and the Chandra deep fields. We had great data from the Cosmos surveys and from Booties, but we didn't have anything wider. So there was a portion of the AGN population parameter space that we were missing, that we were aiming to address with this survey. And then by having the X-rays, this complements what we can learn from the existing wide area optical surveys and infrared surveys. So again, we chose STRIPE 82 for this survey because it's a rich multi-wavelength field, which really complements what we can learn from just X-rays alone. Lots of this multi-wavelength data is just sitting there for us to use. STRIPE 82 is a 300 square degree region along the celestial equator that was surveyed a number of times as part of a Sloan supernova legacy survey. So if you co-add all of those individual Sloan scans, the photometry is about 6 times deeper than the rest of Sloan. So that gives us the opportunity to observe even fainter galaxies to match up to our X-ray sources. And there's already a high level of spectroscopic investment in the area, both from Sloan as well as other surveys that targeted the region. So another thing for folks who work on X-ray surveys know, we spent a lot of time doing spectroscopic follow-up to get redshifts of these objects so we could calculate how far away they are and get their luminosities as well as their spectroscopic classifications. And STRIPE 82 has a bunch of multi-wavelength coverage from the ultraviolet with galaxies, deep optical from Sloan and Hyperset Prime Cam, near infrared coverage from UKIDS and VHS, mid-infrared coverage from WISE, as well as from Spitzer at wavelengths 3.6 and 4.5 microns, and far infrared coverage from Herschel. So this really opens up the full SEDs that we can then characterize of the X-ray sources that we detect. And it's this pre-existing investment, multi-wavelength coverage, that makes Stripe 82 one of the premier large area legacy fields in the sky. Our X-ray data came from both Chandra and XMM, where we utilized archival data that already existed in the field. So the top plot shows the pointings of the X-ray coverage over the stripe. And the bottom plot is the area flux curve, which is the area that the survey is sensitive to as a function of X-ray flux limit. So again, we use existing archival Chandra and XMM data. In cycle 10, we were awarded two specific pointings that overlapped the deep survey in Stripe 82. Each of these patches were contiguous, covering about 2¼ square degrees of coverage. And then in XMM cycle 13, we more than doubled our survey coverage, X-ray survey coverage in the stripe, with about 15½ square degrees with XMM. Where this region was chosen to overlap the existing Herschel and Spitzer coverage in the field. So altogether, we detected just under 6,200 X-ray sources, a significance level of 5 sigma or more, covering over 30 square degrees. And for reference, I'm showing the numbers and the area coverage of two other premier X-ray surveys, the Chandra Cosmos Legacy Survey, which is moderate area, moderate depth, and the Chandra Deep Field South, which is the deepest X-ray survey done to date. And we have been able to calculate redshifts for 97% of these X-ray sources. 56% of these come from spectroscopic redshifts. So with this data set, we can now start providing the X-ray view of high luminosity, high redshift AGN, complementing what we know from optical and infrared surveys. We could start trying to understand the effects these high luminosity AGN have on their environment. We could quantify the obscured AGN fraction at high luminosity and high redshift and constrain their cosmic evolution. And we could start looking at the biases in the different AGN selection functions. All right. So if we focus on just the Stripe 82 X-ray sources that have spectroscopic redshifts, not a big surprise, most of them are extragalactic, though we do get a fair number of stars. It turns out that M stars are not also only very numerous in the universe, they're also really good at giving off X-rays, and they're also very red. So when you're looking for red and obscured objects that emit X-rays, they sometimes end up being M stars. And for the extragalactic sources, most of them are broadline AGN. 20% of them have narrow lines only in their optical or infrared spectra. But for the broadline AGN, I have this little asterisk here to denote that some of these include so-called red quasars that many would consider to be a class of obscured AGN, because though we do see broad emission lines in the spectrum, we don't see a bright blue continuum. We see that there is a lot of reddening to those objects, and oftentimes many, but not all, but many of the bomber lines do show narrow emission features. And I'll talk about this population a little bit more in a few slides. All right, so this plot illustrates how different survey methods complement each other in revealing different portions of the luminosity redshift plane. So we have, so this is X-ray luminosity as a function of redshift, and we're showing here AGN detected from the Deep Pencil Beam Chandra Deep Field South survey, the moderate area, moderate depth Chandra Cosmos survey, and the wide area Stripe 82X survey, as well as the northern portion of the XMM XXL survey, which is another wide area X-ray survey that started around the same time as Stripe 82X. And as you see, at each redshift, as you increase the survey area, you preferentially identify more luminous AGN. So again, it's this high luminosity AGN population that we don't find in large numbers with the smaller area surveys, but we do with the wider area surveys. And this is the parameter space that we want to learn more about with Stripe 82X. All right, so now we could start answering questions like how AGN shape their environment. And one of the major questions out there are whether or not AGN are associated with galaxies that have less star formation, or are AGN quenching star formation. And if you look in the literature, the results are mixed. But if we do expect that AGN are shutting down star formation in their host galaxies, we might expect this to be more prevalent in the more luminous AGN, which are giving off more radiation to energize their environment, and that could be a process by which star formation could shut down. So if this is present, then we would expect to see lower levels of star formation in the hosts of AGN compared with galaxies that aren't hosting AGN. And Stripe 82X is a great sample to test this. And this is something that Brendan Coleman looked at with the Stripe 82X sample. So Brendan is a grad student at the University of Kansas working with Alison Kirkpatrick. And what he did was to work on SCD analysis of Stripe 82X AGN that had Herschel coverage. And so from Herschel, we get the far infrared emission, and this should be a good way to measure host galaxy properties. With the far infrared, we could get a handle on star formation rate and dust mass. And in the XMM cycle 13 coverage of Stripe 82X, that overlaps the Herschel coverage in the field. And there are over 1,800 AGN in that portion of the survey. So what Brendan did was to separate the sample into those where objects are detected by Herschel. There are 120 of those. Most of them were undetected. But what he did was, for this undetected sample, was to bin those objects into bins of X-ray luminosity and redshift, and stack the Herschel data in each of those bins to obtain an average far infrared flux. He then calculated the mean SEDs for each of those bins and fit them with SED3 fit. And so there's a lot of work that he did in that paper. One result that he showed was to look at what was to derive a mean stellar mass based on fitting the SED, and then calculate the star formation that you would expect from a galaxy with that stellar mass if that galaxy was along the main sequence. So typical star formation rates given the stellar mass. And then compare that with the star formation rate from fitting the SED. So these are the results that he found. So what's plotted here on the y-axis is the star formation rate that's measured from fitting the SED versus the star formation rate if that you would get if the galaxy was along the main sequence, given the stellar mass of the galaxy. And that's plotted against the bolometric luminosity of the AGN. So the gray shaded region is where these values are more or less consistent within a factor of 2. Anything above the gray shaded region has enhanced star formation activity, so you might consider that a starburst. Anything below has suppressed star formation activity, so you might consider that star formation rate to be quenched. And so what we can see from this plot is that first, there's a wide range of star formation rates. There's no one typical star formation rate for these STRIPE-82X galaxies. And if anything, we're seeing at the highest AGN luminosities, the star formation rate seems to be higher than it is at the lower AGN luminosities. So we're not seeing convincing evidence that luminous AGN in STRIPE-82X are associated with host galaxies that have suppressed star formation rates. Now, if you're at Ryan's talk last week, you know that the connection between star formation rate and AGN activity is a complex one. There are different time scales. The physical scales are really important. We sometimes see different trends when we look at nuclear regions versus galaxy-wide. And that type of information you can't really unpack from a plot like this. But this does tell us something about the overall properties that we don't see that STRIPE-82X AGN are associated with weaker star formation rates. Another way that we could probe the effects of AGN on their environment is to investigate whether there's a population that's consistent with the merger-induced paradigm of galaxy and black hole growth. And so-called reddened quasars are proposed to be this transitory phase where the AGN is intrinsically luminous but obscured, and it's launching powerful outflows that evacuate the surrounding cocoon of obscuring material. Consistent with the expectations of these models, red quasars are very dusty, but after correcting for dust obscuration, they're intrinsically luminous, among the most luminous AGN at every redshift. Their host galaxies show morphology that is consistent with merger activity. And some of them show signatures of outflows in their spectra. So most of these studies have been on samples of AGN that have been selected based on their radio properties, based on their infrared properties, or their optical to infrared properties. STRIPE-82X gives us the opportunity to bring the X-ray perspective to this analysis. And we do have a little bit of that from the Cosmos survey, an example of which is shown in the bottom right. But Cosmos is a smaller area survey. And if this phase in black hole growth is a short-lived phase, then we expect these objects to be rare. And so going to a wider area means that we should be able to detect more of these objects or more representative sampling of these objects. And this is something that we've started doing. We published a paper a few years ago on our results thus far. One of the samples that we showed was X-ray selected sample of reddened AGN, where we had spectra from Sloan as well as from Palomar triple spec. And we showed that about half of these show pretty significant signatures of kinematics in the narrow line region. So perhaps consistent with this picture of outflows propagating to the host galaxy. We also presented a pilot sample of redder and fainter objects. At that time, we only had 9 out of 36 observed. We're close to finishing the sample. The weather at Keck needs to cooperate with us. Past 2 years haven't gone so well. We'll see how things go this October. But what we did find in that analysis and the data we've gotten since then is that we are identifying obscured, pretty luminous AGN at a redshift greater than 1 that we're missing in our optical surveys and smaller area X-ray surveys. So hopefully we'll have that finished up soon and we can see what STRIPE-82X has to say about the reddened quasar population in this parameter space and how that compares to what we know from other surveys. All right. if we zoom out to the full stripe 82X sample, we could start to estimate the cosmic evolution of obscured black hole growth at these luminosities. And this is some work that Alessandro Pecca has looked at. Alessandro is a grad student at the University of Miami working with Nico Capilouti. And he published this excellent paper earlier this year that has a lot in there. Part of what he does is to do X-ray spectral modeling of the X-ray AGN in stripe A2X that have either good photometric redshifts or spectroscopic redshifts. So he has a catalog where he's released the X-ray spectral fit parameters to those objects. So I highly encourage you to check that out if you're interested. One of the things that he calculates there is the obscuring column density of the AGN. He then does a whole bunch of additional analysis. One of the things that he does is to simulate AGN spectra using the same input models that he used to fit the stripe A2X spectra. And in these input models, he assumed a range of redshifts and luminosities and column densities. And then he saw how many of those AGN would be detected given the stripe 82X survey sensitivity. And then that gives us the ability to derive an intrinsic obscured AGN fraction where the biases of the selection effects of stripe A2X are corrected. So just a note about terminology here for obscured. We're talking about X-ray column densities between 10 to the 22 and 10 to the 24. We're not sensitive to the most obscured AGN, the Compton thick regime, because stripe A2X is relatively shallow. All right, so what he did was to look at this obscured AGN fraction for different X-ray luminosity bins. And what he shows is that for each X-ray luminosity bin, the obscured AGN fraction increases with redshift, and the overall fraction decreases with each of those X-ray luminosity bins. So some of this has been shown in previous surveys, and he's also comparing this with different models, which have a little bit of a wide spread, but nothing completely out of the ordinary. But this is, again, once we, especially when we get to the high luminosity parameter space, this is uncharted territory that we're really able to get into thanks to the wide area survey of stripe 82X. So he predicts an overall intrinsic obscured AGN fraction of about 57% for X-ray luminosities above 10 to the 43 and between a redshift of 0 and 4. And if we go to the highest X-ray luminosities, where we really lose sensitivity from the smaller area X-ray surveys, and go to the highest redshifts above redshift of 3, between 3 and 4, we could start to constrain the obscured AGN fraction, where what he finds is a fraction of about 64%. We could also look at the spectral energy distributions to get a handle on AGN evolution. And this is work that Connor Augie has been doing. Connor is a grad student at the University of Hawaii working with Dave Sanders. And he considers kind of like the full wedding cake population of AGN, combining stripe 82X objects with those from Cosmos Legacy and those from GOODS. So spanning a wider range of redshifts and luminosities. And what he did in this paper that is just about to be submitted was to look at AGN that have X-ray luminosities above 10 to the 43 and spectroscopic redshifts below 1.2. And he made this cut in redshift to make sure that there was photometry to cover the 10 micron part of the SED because this probes the dusty torus emission. He also required that that the X-ray sources had far infrared coverage. So kind of similar to Brandon's work, he doesn't require that there is a far infrared detection, but at least that there's far infrared data there where he could use that data as an upper limit in the SED modeling. And what he did was to divide this sample of AGN into panels that are defined by their spectral shape. So it's spinning it up, and what's plotted here is the median SED for each of those panels. So panels 1 through 3 are defined based on the slope of the ultraviolet emission. So you go down the panels, the UV flux decreases, and in the bottom 3 panels, the ultraviolet flux is completely attenuated. So this is a proxy of the optical obscuration. Panels 3 through 5 are defined based on their infrared emission. So in panel 3, we see pretty strong mid-infrared flux that steadily rises to the far infrared. And panels 4 through 5, the mid-infrared flux decreases, and the difference between panel 4 and 5 is when we see the turnover occur to increase in the far infrared emission. All right. So what he finds is that the shape of these SEDs correlate with the AGN luminosity. So panel 1 are the most X-ray luminous AGN, and as you see, as you go down through the panels, the X-ray luminosity decreases, or the AGN luminosity decreases. And the SED shape is also correlated with X-ray obscuration. So panel 1 is largely X-ray unobscured. Panel 2 also mostly unobscured, though we see slightly higher column densities compared with panel 1. And the bottom 3 panels are the most X-ray obscured objects. So what he's finding is very consistent with Alessandro Pecca's work that the most luminous AGN tend to be less obscured. And it's these objects in panel 1 that are very similar to the optical quasars that we detect from Sloan. They're optically unobscured, they're very luminous, but they're also low in number. In total, this is under 10% of the sample. So if we want to think about having, again, that comprehensive view of black hole growth, we need to expand beyond just optical selection to recover those obscured objects. Also, it's interesting to see how as the AGN becomes more luminous, the obscuration becomes lower, and perhaps this is evidence of an evolutionary paradigm, whereas the AGN increases in luminosity, there's more radiation to evacuate the obscuring material, and maybe these panels represent an evolutionary track going from panels 5 up through panel 1. So hopefully his paper will be submitted soon and you get to read through it after it comes out. All right, so now to return to a topic I brought up at the beginning, which is how different multi-wavelength selection methods identify different types of AGN. There was a project that we had that provides a really good data set to look into this in more detail. Several years ago, we had a program within the Sloan Digital Sky Survey, a spectroscopic program to obtain spectroscopy of X-ray sources in stripe 82X. So if we go back to our X-ray coverage map, it was this area of stripe 82X, which is the largest contiguous area, that was targeted as part of the Sloan survey. So what we did was to put a spectroscopic fiber on every Sloan counterpart to an X-ray source that didn't have a redshift. And we also put fibers on mid-infrared selected AGN that were selected based on their WISE W1 minus W2 colors, where W1 is the flux at 3.4 microns, W2 is the flux at 4.6 microns. And at the time, this was the largest spectroscopic survey of W1 minus W2 selected AGN. So this gives us an opportunity to see how well this selection works at identifying AGN. So quick summary of what we found. Over 2,700 AGN were spectroscopically identified through this survey, and the fraction of those that were obscured were relatively high. Now, for the X-ray sources, it's really clear what these objects are that are lacking broad lines in their optical spectra. We have the X-ray luminosities, they're above 10 to the 42. These objects are clearly AGN. For the WISE objects, it's a little bit less clear. What we know is that these objects have red, mid-infrared colors, and they don't have broad, for the ones that I'm labeling here as optically obscured, we know that they don't have broad lines in their spectra. So are these obscured AGN, or are these star-forming galaxies that happen to have red colors? And one way to get a handle on that is to use optical diagnostics that parameterize the strength of the ionization field and the metallicity of gas. I'm sure many here are familiar with the BPT diagram. So anything above the dashed Cooley line is surely an AGN. Anything below the dotted Kaufman line, at least optically, would be classified as a star-forming galaxy. So when we looked at our mid-infrared sources that didn't have broadline in their spectra, we found that half of them are in the star-forming locus of the BPT diagram. So this then begs the question, are these star-forming galaxies that are masquerading as AGN? Or are they deeply buried AGN that are so dusty we're not seeing optical signatures of black hole growth, and if they're Compton thick, we're not seeing X-ray emission from them either. This was something that Antonis Georgakakis looked at in a little bit more detail. Antonis was second author of this EBOS paper. And what he did was in this follow-up paper, was to do some empirical forward modeling where he created these mock galaxies that he seeded with AGN, and then he tested the WISE and X-ray selection of these mock galaxies. And what he found was that the WISE selection was contaminated by a relatively large number of star-forming galaxies at redshifts below 0.5. So for these objects, some of them probably can be very heavily obscured AGN, but some of them might not be. If we really want to know the answer, there are mid-infrared spectroscopic diagnostics we could use, and there happens to be a telescope in space that's got great mid-infrared coverage that could help us answer this question. And I think this is an important question to answer, because if there is a high level of contamination of star-forming galaxies in the local universe, mid-infrared selection, this has our implications for our understanding of obscured black hole growth, because those numbers could be biased high if we're not correcting for that contamination. Another thing that we looked at in the paper were the types of AGN we selected or we identified based on their X-ray properties, and those that we identified based on their WISE colors and what the overlap between the two are. And only about 25% agree between the X-ray and WISE selection. And in the paper, we kind of dive deep and we talk about which ones we detect in one method and not the other. So I'll refer you to the paper for more details. But one result that struck me was to look at the X-ray AGN that weren't detected by WISE. So these weren't objects that were detected by WISE, but their colors were too blue. These were things that WISE didn't find at all. And I wanted to know what those looked like in terms of their luminosity and redshift properties. So on the left is a plot of all the X-ray AGN in stripe 82X. So X-ray luminosity versus their redshift. No big surprise, we're skewed to higher luminosities because those are the types of AGN that wide area surveys preferentially identify. And I asked, where do these WISE dropouts live in this parameter space? And I expected they would all be at lower X-ray luminosities. But when I did that, which is the plot shown on the right, I found that wasn't true. They're predominantly at higher luminosities. And this was a surprise to me because the conventional wisdom is that mid-infrared selection identifies all the luminous AGN, and here's this population of luminous AGN that WISE doesn't find. Now, this could be related to survey sensitivity. Maybe the X-rays are going deeper and are picking out more luminous AGN that are at fainter flux limits that WISE doesn't see. Or maybe this is a population of objects that have anomalous mid-infrared properties because they don't have much dust. Perhaps they are a population of what's called hot dust poor or hot dust deficient quasars. And it's been proposed that these types of AGN don't have much dust because they have a low Eddington ratio, which prevents the torus from forming. This was a question we started investigating with a grad student at JHU. And there's more work that we need to do before we could say more about this. But what I like about this result is that it illustrates how Stripe 82X gives us the opportunity to identify populations of AGN that don't adhere to the standard model, and what that might teach us, not just about the diversity of the AGN population, but to also test accretion physics models. All right. So with wide area surveys like Stripe 82X, like XMM XXL, like eROSITA, which is all sky, as well as moderate area surveys like XSERVs and BOOTIES, we're getting the data to fill in the X-ray perspective of the high redshift, high luminosity, obscured black hole growth. For Stripe 82X itself, we're not finding that the AGN reside in host galaxies that have suppressed star formation, but the reddened quasar subpopulation might be providing feedback into their host galaxy. We are finding, consistent with previous studies, that the obscured AGN fraction increases with redshift and decreases with luminosity. As the first time we have statistics of this population at X-ray luminosities above 10 to the 45.5 and redshifts above 3 to start estimating that obscured AGN fraction. Some fun stuff coming up. I've calculated the black hole masses of the Stripe 82X AGN that are unobscured and that have spectra in Sloan. So I'm working on a catalog release paper now that has those black hole masses, as well as the additional spectroscopic redshifts we've gotten with more follow-up that we've done over the past few years. Hopefully, we'll be completing the Stripe 82X reddened quasar studies soon if things go well with our Keck observing run in October. And Alessandro Pecca is leveraging new archival Chandra and XMM observations that have become available in Stripe 82X over the past decade, and that will increase the survey area to 55 square degrees, give us about 1,200 X-ray sources, and these data, along with data from the other wide area X-ray surveys, will help us to complete the picture of the evolution of high luminosity, high redshift obscured AGN, and better understand the role that they play in shaping their environments. So thank you very much.
Great. Thank you so much, Steph. Let's give Steph a round of applause for that excellent talk. It's really showing the power of these wide area X-ray surveys and very nice results. So questions for Steph? Sorry, I'm trying to find my gallery view here. Ilse?
Hello. Hi, Stephanie.
Hello.
Yeah, good to see you. Yeah,
Good to see
very
you
good
too.
talk. Yeah, I enjoyed a lot. I'm just curious, because I'm from the radio community, whether you would have a chance to look at the Stripe 82, which could have some, overlap with the first, the radio survey. I mean, even though there is no direct detection, you could stack or something. So I was just basically curious how these X-ray properties correlate with the radio emissions. I mean, if you, for example, put them in the black hole fundamental plane, for example, are they all consistent, or do you find some systematic trends depending on the radio luminosity? Do you have any comments?
Yeah, so that's a really, really good question. So one thing I didn't mention is that we also include first data in our catalog. So those are for the detections. We haven't yet done that, but that sounds like an excellent project to look at, both in terms of the stacking and individual detections, and see how the radio and X-ray properties compare with each other. So let's talk offline. Maybe we could find someone who could take on that project. I think that'd be a very interesting thing to look at.
Oh, I see. Yeah, sounds very great. Thank you.
Thank you.
Great, thank you, Sang, for pointing out the radio side of things. Ryan?
Hey, Steph.
Hi,
Thanks for
Ryan.
the talk. I was curious about your WISE non-detected things that you mentioned. One thing I know, and you may have mentioned this and it may have gone past me, but one thing I noticed, the luminosity looks about the same as the whole population, maybe slightly higher, but but they're preferentially found at significantly higher redshift. It looks like it peaks up around redshift 2 instead of like redshift 0.5. Could some of this be just a sort of K correction that you're probing a different part of the SED? And if you like, I guess, is there anything, or maybe this is what you're working on, but if you forward model this through, do you have a sense of whether these would be these higher redshift ones in particular would be substantially different from the others?
Yeah, so that's a really good question. So we haven't looked at the forward modeling. So the project that we were doing was to fit the SEDs of these objects and then compare them with SEDs of typical quasars and hot dust poor quasars, and just kind of see where things fit in, because that is that question, right? Like, is it, is it a flux limit thing? Is it what we're seeing? Is it a K correction in the spectrum? So for the hot dust poor quasars, I think these were first found in the Chandra Cosmos Legacy Survey. And one of the points that they made was that it was the near infrared emission that seemed somewhat suppressed compared to normal quasars. And if you look at the redshifts of where these things occur and where they're falling out of WISE, that seems to kind of line up. So we were hoping that by using SED modeling, we could get a handle of what the physics might be that's driving it.
Great, thank you.
Sure.
Great, thanks, Ryan. Actually, can I ask a quick follow-up to that?
Yeah.
Because that is a weird, interesting population. I mean, if they're not detected by WISE because they're somehow hot dust poor, I mean, wouldn't they be broadline objects? And do you have spectroscopy on those?
Yeah. So we have spectroscopy for all of these, and these are all broadline objects. So that was the way that the project was kind of set up. Like, first, all right, not all of these are broadline objects, but what we selected to study for SED analysis were the broadline objects, and then compare that with like a control sample of broadline X-ray AGN from Stripe 82X that are detected in WISE, and trying to understand what the differences might be between the two populations, and then also between canonical SED models.
Mm-hmm. Oh, great. And Gabby?
So now I have a follow-up on that.
Okay.
So is it possible to choose, do sort of the same selection, but with type 2s and see how, do the same analysis and see if you also, with type 2s, if you also find these non-WISE emitting objects?
Yeah, so there's Steph, so in this plot, there are both type 1 and type 2s. If I remember correctly, they're mostly type 1s, but there are a handful of type 2s in there. When we were doing the SCD follow-up project, we kind of discarded those from the immediate analysis just to make the project a little bit simpler, but it's definitely something that we can look at for sure.
Because those wouldn't be hot dust poor quasars, right?
Right, right. And I forget what the breakdown is. It wasn't a large number of type 2s. So those could have been ones that, perhaps are just fainter and WISE doesn't pick them up.
Great, thank you, Gabby. And so one last question, Dana.
Yeah, hello, thank you.
Oh.
Thank you for the talk. I always concerned about angular resolution, and I was wondering whether that's worry you. And because you combine the whole electromagnetic spectrum, super great, but of course, very different angular resolutions. And in particular, in this plot you are showing now, in the infrared, it matters a lot. In the X-ray, you don't have resolution, but X-ray photons are expensive and mostly they will sample what is the AGN because are very hard. But the infrared, you have the host galaxy as well. It must be contribution of star formation. And in cases where, and we know a low ratio, where the AGN is faint, it would, and that implies how WISE classify objects on the basis of the resolution it has. You might completely miss plenty of AGNs. You might see the X-rays because there is nothing that will worry them, but it will be very hidden in the infrared. Just because of resolution, just because the AGN itself in infrared could be faint, just because the galaxy overtake this emission. And
right, so
won't classify it as AGN.
Yeah, so I absolutely agree with that. So what we did when we created the multi-wavelength catalogs for Stripe 82X is, we have our list of X-ray sources, and then we just match that up photometric to these other photometric catalogs. So at that point, we don't care how something else is classified in the other catalogs. So if it has a detection in WISE, then we take it and we use that data. So unless the object, like something like this, isn't detected in WISE, and maybe that's because it's just too faint or whatever, we have that WISE information. So then the question becomes, how much of that WISE data or WISE photometry or flux is coming from the AGN, and how much of it is coming from the host galaxy. So for the projects that we've worked on within the group, we quantify that through the SED analysis to try to disentangle and decompose the relative process. But you're right, if we had better angular resolution, then we could do a better job of saying what's from the AGN and what's from the host galaxy.
But even if you don't detect that, because you say, I'm going for any detection in WISE that I suppose that might correspond with your X-ray counterpart. It could be that in X-rays could be very strong emitter, but in infrared, no. And this you have many cases in the low universe, in the near universe.
Right. Yeah, and to me that's interesting, because that's telling us something about the SED, right? So if this something is super bright in X-rays and not super bright in the infrared, that we don't even detect it, then that's interesting. And so it's not saying that there's not infrared emission there. It's just saying that the SED that we're observing for those objects is different than the canonical SED that we usually assume for AGN.
Well, it might be similar to AGNs that we have in the local universe. They have this particularity.
Right.
Strong X-rays. It might make one single question. Do you have an idea for these cases? What is the mass of the galaxy?
So
I don't have dwarfs in between.
Yeah. So I don't have the galaxy stellar masses off the top of my head, I know that that has been a byproduct of some of the SED modeling that's been done by some folks in our group. So but I'm not sure if those results have yet been published in catalogs or if they've just been used in an aggregate form. So I don't know if that we have those publicly available, but that's not something that I've looked at particularly in the projects that I've been leading or I've been working on with students.
Thank you.
Sure.
Great, thank you, Almudena. So let's give Steph a round of applause again for that wonderful talk. It really is highlighting the power of wide area X-ray surveys and a really nice set of results here. So Jeffrey put a link in the chat for anyone who wants to join. Steph, I don't know if you have time to talk to students for a little bit. Afterwards, just click on the Zoom link, and I just wanted to thank Steph again for that wonderful talk, and on behalf of all the seminar organizers for this series, I wanted to thank all of the speakers who spoke this year in the seminar. It was really an inspiration, and I want to thank the audience for joining us for this engaging discussion and questions. And I wanted to wish all of you a wonderful, restful summer, and cheer on the people on the West Coast who are still teaching. Go, you're almost there. So have a wonderful summer, everyone. It's been a pleasure.
Thank you for organizing everything.
Bye.
Thank you. Thanks for organizing all this.